So here in section 10.4, we want to look at areas and lengths in polar coordinates now. So we know how to find the arc length of a curve or the area inside a loop with parametric equations. We want to be able to do the same thing with polar. So here's the idea. Let's say that we've got this polar curve here. So this is r equals some equation in theta. We'll call it f of theta. And we're going to mark it off here with a starting angle and an ending angle, like so. So we'll call that angle here alpha. And then the ending angle here, we're going to call beta. So again, that's from the positive x-axis. So then what we're going to do, we want to know, what is this area equal to? So what is this area in here? There, I think I can put some paint in there now. There we go. So we want to know, what is that yellow area? So what we're going to do is we're going to partition this up into a whole bunch of little pieces, little slices of pie here. So just like when we're doing things in Cartesian coordinates, we might partition along the x-axis. So here we're partitioning the independent variable, which is theta, which is an angle. So we divide this up into a bunch of little sectors. And we know how to find the sector area of a circle. That formula, although you might not be familiar with it, you should have used it somewhere in pre-calc or algebra 2. 1/2 r squared theta, where theta is the angle that you rotate through for that sector. So for a whole circle, theta is 360 degrees. So what we're going to do is we're going to take one of these sectors, bring it over here, and talk about how do we approximate one sector. So that might look something like this. And then let's see, that f of theta looks something like that. And then what we want to do is we want to again, these angles here are going to, you have a starting angle and an ending angle, and we are going to name this delta theta sub I. So we pick out the ith slice of this, and then we want to approximate it. So there is some starting and ending angle here for those two pieces. This is the change in the angle. Then what we do is we pick a partition point. So some angle that's between the two ends there, say it looks like this. And that's what we'll call theta I star. So the star is saying it's a sample point from somewhere in between here. Well, that determines a radius right here. So we can find the sector area of a circle that has that radius. So let me do that point in black. So radius right there. So the area of this slice of pie is approximately equal to the sector area right here. So what we've got is here the actual area. Let me put that in blue. So your actual area is a sub I, and that's the ith sector. And we're going to approximate a sub I with 1/2 times r sub I squared theta. Okay, that comes from this. So we need our radius function, but our radius function was given by taking theta going out to the equation of r equals f of theta. So actually this radius here is f, plug in that sample point, theta sub I star. So right here we got r sub I squared. We took our theta sample point and plugged it into f. So here I denoted it without the star, and then squared it. And then this is change in theta. Now if we make all these the same, we don't need to subscript it with an I. And that's what we did here. So the area of the ith sector is all in terms of theta here. So if you're going to find the total area, you sum up all those sector areas. So sum up all the areas of these pieces, well actually the sectors that are approximating them. So our total area is going to be approximately equal to the sum of the pieces, little pieces of sector area of a circle summed up. And then each one of those pieces is approximated by 1/2 f of theta sub I squared times delta theta. So then if you look at a limit here as n goes to infinity, then our actual area will be the limit of this guy. So your 1/2 comes down, f of theta sub I at a sample point turns into f of theta, delta theta into d theta. So this is sector area of a circle, and then the integral adds them up. We'll abbreviate that formula with 1/2 r squared d theta. So that's where it comes from. It comes from sector area of a circle. So now let's try an example here. So we want to show that the area of a circle of radius 3 is pi times 3 squared, which is 9 pi. Okay, so if we sketch what's going on here. X and Y axis, got that circle of radius 3, looks like that. So the equation of this is r equals 3. So for any theta that we pick along here, the radius, which looks like this, is always going to be equal to 3. And that's for any theta in here. So no matter what your angle is, r equals 3. That's our f of theta. That's the same thing as f of theta. So let's go ahead and set up our area integral. So area is going to equal the integral of 1/2 r squared. Okay, r is 3, so 1/2 times 3 squared. Then times our, so we got 1/2 times our r squared, and then d theta. And then we're going to add up these little slices of pi. If we slice the circle all the way around, we are going to add those slices of pi up from 0 all the way around to 2 pi. So what I did to get those limits of integration is I let a general radial segment sweep over the area. So you let your radial segment sweep over the area. And then the limiting positions that touch the region are 0 and 2 pi. So 0, 2 pi are the limiting, or the limit angles that touch the region. Okay, and that's always how you want to get your limits of integration. So I can show you a quick Mathematica demonstration to show actually what we're doing when we let the radial segment sweep. So here I have a Mathematica demonstration that will show that general radial segment. So here's that radial segment from the center ending out at, this is our f of theta is r equals 3. That's the one we're working on. And this is what you want to picture in your mind. That segment sweeps over that. So you're adding up all those little slices of pie there. And then let's look at a few others here. So if we have a circle this is a cosine theta circle. So theta is only going to go from 0 to pi here, but we watch it sweep over the area. So that first, and then this with a negative radius. And then keeps working that way. Let's see, circle over here. This one's going to be 0 to pi. This is a little more straightforward. So right there you see the radial segment sweeping over the area. It's adding up those little slices from angle 0 over here to angle pi. And let's do one more. So here's 4 leaf rows. It's 3 cosine 2 theta. And watch how it adds up the slices. So again, some positive radius, some negative radius there. But yeah, it's just adding up those slices of pi as you let that radial segment sweep over the region. Now, one thing to notice with this one, and we'll consider something like this, is that you have symmetry. So this piece here is the same as this one here. So you really just have to find the area of this piece and then multiply it by 8 because all the petals are the same. Okay, well, back to our problem. Finish up. This is an easy integral. So we've got 9 halves, which we can pull out in front. And then we are integrating from 0 to 2 pi. All that's left is a 1 d theta. So if we integrate that, we get 9 halves theta. Theta is going from 0 to 2 pi. So that is 9 times 2 pi. 9 halves times 2 pi, which is 9 pi. And that's exactly what you get if you do pi r squared. So we showed that this was true for a circle. We proved the area formula for a circle. So why don't you try in section 10.4 problems 1.2 on the website? Give those a try and see how this works out.